Do you see my screen?
I'm afraid not.
What now?
I'm not sure it's just me, but I don't think I see you. Oh yeah, now I see it. So
Okay.
yeah, it must be.
Hello, my name is Ashkbiz Danehkar. I'm a research scientist at Eureka Scientific, and my research is about measurement of spin of supermassive black hole in Seyfert 1 AGNs. And I recently used principal component analysis to evaluate whether X-ray variability has any effect in spin measurements. This is the outline of my talk. I briefly talk about the spin measurements and also modeling X-ray reflection emissions and spin measurement from Bayesian statistical analysis and whether X-ray variability affected spins. And also I will evaluate it if spins X-ray variability affects spin using the principal component analysis. And here is a brief implementation of spin for AGNs. It is believed that spin has some effects on outflow from in AGN on radio load and radio quiets. And in radio load, some people they believe there is a negative spins, and in radio load quiets also, and the intensity of the outflow could be affected by the spin value. There are different methods. There are different methods for measurements and X-ray reflection modelings. Currently is the best method for AGNs, and also there is a fitting UV continuum, but needs a high quality UV spectrum, and also quasi-periodic oscillation modelings, which in under development, polarimetry also under development, and event horizon imaging is only suitable for nearby AGNs. And in X-ray reflection emissions, you see different type of K-alpha emissions, Newtonian special relativity and general relativity, and general relativity blue lines. And due to light bending and frame deragging effects, and also gravitational lensings, we have those things you see in the on the right in the simulation by Dowder in 2010s, and by integrating this image of accretion disk, we can constrain the different value of spins. The negative spins due to frame derivative effects, when the accretion disk and spin has opposite direction, we have higher inner radius, but in the maximum speeds, we have lower inner radius. So this have implication for measurement of reflection emissions. And here you see the typical X-ray spectra, and the continuum is related to corona emissions. And on the blue lines, there is the feature which you see by relativistic Browden K-alpha emission line, and the orange is related to distance emissions. So by combined modeling, we can constrain spins. And I use this model, absorb power law plus Rayleigh and Silver. Rayleigh is for innermost region of black hole where there are relativistic emissions, and Silver is non-relativistic related to distant part of accretion disk. And also there is another model, which a new model, REL-ZIL, which is combined power law plus relativistic emissions, and Silver is for also distance emissions. And here you see we are able to constrain the spin of black holes. And I use the Bayesian statistical analysis to perhaps the higher and lower limits for spin value, inclinations, and the power law index, and iron abundances. And we fit using a model, and then you use those per your knowledge to obtain the 1 alpha, 1 sigma, and 2 sigma, and 3 sigma constraints on the different parameter spin and is inclination and photon index. We have also photon index here, and we have ionization parameter of Rayleigh, which is for inner region, and Silver for distant region. And however, there is X-ray variability in AGNs. For example, for this one, NGC 3783 in the 2001, it was in bright and soft state, but in recent observation, you see in 2001 it was in the bright and hard state, and in a later observation it's moved to harder and fainter states. And this kind of variability is believed in this Seyfert AGN related to transient obscuration events, which likely made by an ecliptic outflow near X-ray source. And in other AGNs, we have, for example, PDS 456. There are some yearly variability, which is believed related to failure rings in corona, and something similar to what we see moving from low or hard state to high and soft state in X-ray black hole binary. So this kind of variability, which you see here and here, may have some effects. This is a question if whether it has effect on SV measurement. I use a principal component analysis, and this method is a method technique for decomposing temporal variable data. And in this work, I use a code which developed by Mike Parker, and it is based on single value decomposition function of NumPy, and it's give us principal component, which is X spectra. Here in U is principal component, and there is diagonal matrix, which is eigenvalue, and we also have another matrix is the eigenvector. Eigenvector presents the light curves, and using the eigenvalue, we can find what is the fraction contributions of different components. For example, here you see power law normalization has the bigger contributions, and red is photon index. Second component has also a contribution, and the reflection emission has a low contributions. Here on the percentage is shown on the left plot. Normalization's factor of power law has 99%, and photon index of power law has 0.5%, and reflection emission has 0.3%. So reflection has a very low contribution, and most variability is related to X-ray emission power law from corona. And the previous study was for XMM, and this is for Suzaku. Also, I did this study for Suzaku. To implement into this study, I use all available archival data of Suzaku, and I produce time slice data at 10 kiloseconds, and I use those data using those package principal components analysis Pythons. And here you see you have power law normalization factor has 92%, and power law index has around 3%, and reflection against is around 2%. So reflections variability is very low, and I should explain on the right eigenvalue plots. Those higher value, which have we see a linear correlation on higher value, likely related to background noise. So as you see here, there is a very small fluctuation in the reflection emissions, and the X-ray variability mostly come from X-ray source, which described by power law motors. And this small variability in the reflection emission could be related to light bending near event horizon. Here is a simulation from event horizon telescopes, and as you see, there is a small variability in event horizons. And I also extracted these third components, which related to reflections. And when we extracted from principal component analysis, it gives us a text format file, and I converted this text format file to a file which is compatible for studying expect package. And here I fitted a reflection emission, and the value which I got was 0.97, which is the same as value which we got with a Bayesian statistical analysis. And in summary, or principal component analysis implies that extra variability mainly related to change in continuum of power law emission source, and tiny variability in relative reflection emission, likely made by light bending and near event horizons, and variability has no effect on spin's value. And supermassive black hole spin remain constant over time of humans time scales, and it is not affected by variability in AGN, and spin value derived from principal components of reflection emission is consistent with what got with Bayesian statistical analysis. And if you have any questions, you can contact me. And this research supported by NASA ADAP grants. I appreciate for giving me time to present my works. And if you have questions, I can answer.
Thank you so much, Ash, for a great talk. Do people have questions? We still have 1 or 2 minutes. See anything posted in here? I'm just quickly ask a small question. Like, I may have missed this from the beginning, but what kind of data did you do the PCA on again? Like, what kind of format of data did you use for this analysis? And yeah.
It's X-ray data, you mean? X-ray observation. It was archival or available archival for each object. For example, NGC 3783. I use all available XM Newton archival data, X-ray data, collected by XMM telescopes.
Like, does PCA just like effectively reduce the generation?
In PCA, I extracted this data and I've been the data. It is called. I produce time slice data at 10,000 seconds, and I use those data. I supply to here. I can show in this diagram. I supply to this package. This package using. I produce this matrix A, and this matrix A is a time series of and time slice spectra bin with some energy bin. I use 100, and I use this single value decomposition. Principal component analysis usually used in machine learning to simplify data on unsupervised machine learning. So this provide U is a spectra, and on the middle diagonal matrix is eigenvalue, and V is a eigenvector, which is light curve. But we see here on the right is principal component spectra, on the middle is light curve, and on the right is eigenvalue.
I see. Yeah, thank you. Thanks so much. We may have to move on to the next speaker, but yeah, thanks so much for your talk. Yeah, thanks, Ash. Our next speaker will be Jianhan Zhao from